So now that we've done lots of stuff with integrals, I want to start talking about some applications of integration. And these are physical applications. And one of the easiest ones to do is applying that to the physical concept of work. So you might remember from a basic physics class, physical sciences, whatever you might have done in the past, that work is equal to force times distance. Right? So the units on work are joules, right? Which is usually abbreviated with a J. And this is equal to, Newton meters. Newton times meter. Right? In the imperial system, you might know these as foot-pounds of torque. Right? So, how do you compute work? Well, if it's done in a straight line with a constant force, so if we have constant force, not constants, constant force, with what we call magnitude F. So let's just say the constant force is F and the distance is D, then work is just, again, force times distance. But, when it comes to applying a force, think of, think of pulling a wagon, right? You might sometimes pull it really hard. You might sometimes pull it softer. And let's even just assume we're just pulling the wagon straight down a street. There's no reason, that we have to pull it with a constant force. For example, like imagine we're pulling this wagon a really long distance, and at first, you'll be full of energy and the force you'll pull with is pretty high. But maybe, as you get tired, the magnitude of that force you can pull with starts to go down a bit, right? So how do we handle the case in which the force is variable? All right. Well, what we can do is imagine here that what we're going to do here is we're going to say X is the direction that we're pulling the wagon, or whatever you want to think of it as. And here I'm going to graph force versus distance. So X is going to be distance traveled, okay? And F is going to be the force applied after having traveled that much distance. So let's say, your force is something like this. Right? You start out a bit slow, then you peak, and then maybe you start getting tired or something like that. Right? And you want to know how much work was done from this point here, A, to this point here, B. All right? So how can we find this force if the force, this work if the force is variable? Well, what we can do is say, all right, well, this force is variable, but I'm going to approximate it, right? So what we're going to do is say, well, let's cut up the distance traveled into little segments, okay? And then on each of these segments here, right, I'm going to draw a line up to the force function. And what I'm going to do is say, all right, in here, I'm going to, in this little chunk, I'm going to approximate the force as a constant. And I can approximate that however I want, right? I can take the low end of the force, the high end, I can do some kind of average. So let's say, we just take whatever it is at the start of that distance segment. So here, this would be the force value. This would be the force value. Here, 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 and here. So what I'm going to say is on this segment here, this little segment of distance, I'm going to approximate the variable force by this constant value, right? And then the area of this rectangle will represent the force on this little segment. This will give you force 1, or sorry, not force. This will be the work done over this little segment. Work 1, work 2, work 3, ... work n. So if this looks familiar, it's because it should. The amount of work done is in fact just the area under the curve. So, without getting into all the little details here, work, let's say, maybe I should write it like this. The work done by a variable force f of x from position x equals a to x equals b is given by work equals the integral from a to b of f of x dx. Right? So to find the work done by a force over a distance, we just integrate that force function over the distance of travel, over the displacement, right? And so the area under the curve here, in this particular instance, is equal to the work done by that force, right? So let's look at some common examples of force functions. Okay. So one of the most common ones of a variable force is the force supplied by a spring, right? To stretch or to compress a string, right? If you've ever had a long enough spring, as you start compressing it from its natural length, you'll know that, well, it starts to get harder and harder to compress, right? It starts to push back. And that's because it's a variable force. So that's measured by Hooke's law. So Hooke's law, right? So here, we say F, this is the force required to stretch or compress a spring. Okay. K is going to be the spring constant. And of course, D, let's use X. X is going to be the distance compressed. All right, or stretched. All right. Then Hooke's law says that F is equal to K times X. So it's a simple linear relation here, right? Simple linear force. But here's a classical example of a non-constant force, right? Another one you might be familiar with is the law of gravity. So Newton's law of gravity. So here, F is going to be the force of attraction between two bodies of masses m1 and m2, right? And Here we're going to say x is the distance between the bodies. Distance between bodies. Right? Really, it should be sort of the distance between their centers of mass, so to speak. But normally when we apply this in like simple situations, we think of these as point masses. Right? Anyway, so F here is going to be G m1 m2 over x squared. Right? Let me box this. I actually forgot to say here that G is this universal, I think it's gravitational constant. Right? And the units on this, if you are interested, are about this is approximate, 6.67 times 10 to the minus 11. So this is meters cubed times kilogram. Oops. Oh my god, my whole thing went away. Sorry, that kilogram's supposed to be on the bottom. Cubic meters per kilogram second. All right, so and some interesting units on this, but yeah. All right, and one more that is actually kind of a cousin of this formula right here is something called Coulomb's law. If I could spell Coulomb, right? Sorry, spelling is hard. Coulomb's law. Right. Let's make this actually look like a O. Coulomb's law. All right. So here, F is going to be the it's again the force of attraction, but in this case it might also be repulsion between two particles with charges Q1 and Q2, right? And here K, this is known as Coulomb's constant. Sorry, forgot I had an alarm going. So, wow, one day I'll spell this. So this is Coulomb's constant. I actually forgot the units are the value of this one. Let's look it up real quick. So Coulomb constant. Forget the units on this. Where are you going? All right, and this is about 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. All right, do some nice units on that. All right, and the law here is actually basically exactly the same as Newton's law, which is pretty interesting. Oh, I forgot to say x is the distance between the particles. See, I just have to forget one constant each time. All right, so these are some examples of non-constant forces. And we'll do some computational examples in a bit.